For being back for this Thursday lecture. Today we have the absolute pleasure of having with us Bálint Koczor. Bálint is a Gladstone Research Fellow at the University of Oxford, and his research covers both practical and more fundamental aspects of quantum computing. He's a senior quantum theorist with quantum motion technologies and a research fellow at Lady Margaret Hall in Oxford. I've had the pleasure of reading many of Bálint's work, some of which he's going to be talking today. So without any further ado, Bálint, you have the floor, and thanks again for joining us.
Yeah, thanks very much, Marco, for the kind introduction. And let's get to it. So today I'd like to talk about how can we deal with errors in quantum computer. And so you might have heard about quantum computers a lot recently. You might have heard they are very useful, or might be, or will be very useful. And you might have also heard that companies are building larger and larger, extremely complex quantum computers, such as Google and IBM and so on. And they've even gone as far as demonstrating supremacy. In principle, we are now in the regime of quantum supremacy, where we have extremely complex quantum computers that we cannot even simulate classically. However, the big problem is that, and this is one of probably the most pressing issues with quantum computers, that they are still very noisy. And so for a supremacy demonstration, it was actually part of the demonstration itself that the quantum hardware has noise. And as you can see on this plot, the fidelity with respect to the ideal state decreases exponentially. So this is a logarithmic plot. And on the x-axis, we have the number of qubits that are operated on in this quantum processor. And so you can see that the number of qubits was as high as 50 plus. But unfortunately, this fidelity, which expresses how close we are to the ideal computational output, it decays down to a fraction of a percentage. And that's a huge loss. Basically, we lose almost all information. And what comes out of the quantum processor is basically white noise, or almost white noise. So we have to do something about this. And this is a very important problem that we face now. The solution is actually well known. So we need to use quantum error correcting codes, because these quantum error correcting codes can catch errors on the fly and correct them. And these are actually very well established techniques. Already in the 90s, people started to think about what can we do about errors. And they came up with all these kinds of highly complex codes. But collectively, these all can suppress errors to any desired level efficiently, where efficiently means that we only need to pay a polylogarithmic price when we want to suppress the errors in the qubit count. So this also means that we have to introduce redundancy in our system. So it's similar in some sense, similar to classical computing, because in classical systems, when we have a bit string 001, for example, if we introduce redundancy, we can represent every bit by, let's say, a pair of bits. And there we can identify bit flips and correct them. And so a very useful measure is the parity of a bit string. We can check the parity, and there are well-established techniques to do that in classical computing. However, the quantum analog is highly non-trivial, and it's much more complicated. But it turns out the worst part is that we have to pay a huge price, because quantum mechanics does not allow us to actually read the bit string. Because whenever if we tried to access the information within a quantum state, we will collapse into one of the eigenstates. So quantum mechanics does not allow us to read the bit string and identify errors. But we can, in some sense, trick quantum mechanics and encode the quantum information into a huge, highly complex entangled quantum state. This is a so-called logical qubit. It's encoded into many physical qubits. And so the smallest possible instance is 5, meaning that we need 5 physical qubits to encode just a single logical qubit. And on top of that, we have to do highly non-trivial additional measures. For example, we constantly need to monitor our quantum state, whether it's still in the logical code space or not. And we cannot even identify by this where the errors happened. So we need to have an extra complexity, like a classical supercomputer that figures out to which qubits the errors happen to. And on top of that, we even need to do magic state purification, which I will show you in a bit. It's a highly non-trivial thing to do. But all of these, or any of these, are basically prohibitive for the NISQ, for the early quantum computers, the ones that are coming out. And probably these quantum error correcting codes will be prohibitive for the next years to come. And just to illustrate why, so some error correcting codes have been demonstrated in experiments, but so far these were limited to error detection. Basically, researchers were capable of encoding the logical quantum bits into physical bits, and they were able to monitor whether errors happened or not. And when they identified errors happened to the system, they just aborted the computation. And these were implemented so far in experiments, but earlier this week a paper came out by the Innsbruck team, and they are, I think, the first ones to implement an actual error correcting code with all the fault-tolerant ingredients. So fault tolerance means that we not just need to do this extra hassle with quantum error correcting codes, but whenever, for example, we read out the errors, we need to do that in a fault-tolerant manner. That means if we have errors in the measurement process as well, that will propagate into our information about the system. So we need to also do something about it. And if we can do every single operation, every single step in our code in a fault-tolerant manner, then we can say we have a fault-tolerant quantum computer, and we can, in principle, operate this indefinitely long. In this ion trap demonstration, they had 7 qubits, so 7 physical qubits to encode just a single logical qubit. But this can be considered as kind of a baby example for what we actually need in the future. So for solid-state systems like Google's and IBM's quantum computers, we will likely need more than 1,000 qubits per single logical qubit. And that's prohibitively costly for the near future. And that's why people have been looking into how can we achieve value with the already existing noisy machines without paying the huge price of quantum error correction. And one answer is basically we need to use shallow circuits. So the error corrected circuits that we will likely use in the far future, and which we'll be able to implement, for example, Shor's algorithm. So they will have extremely deep quantum circuits. So that's why we need to be able to basically run computations indefinitely long. However, if gates pick up noise, then we see an exponentially degrading information in our system. And if we are able to limit ourselves to shallow quantum circuits, the impact of noise. And so it turns out these shallow circuits are extremely useful in the sense that parameterized quantum gates are very hard to do with error correction. But if we just use the bare physical qubits, like this, we can actually, in the experiment, really straightforwardly implement any continuous angle rotation. For example, here, every quantum gate is a rotation gate, basically. You can think about this as an X rotation of the Bloch sphere. We can implement the X rotation for any continuous angle. It's really straightforward in an experiment because basically we just need to set the timing of our laser. And it also turns out if we are able to implement these continuous angle rotations, we can rapidly generate very complex quantum states, which we cannot even simulate classically if we have enough qubits. Let's say the barrier is typically considered as 50 qubits for the entry-level problems. And so the idea in general with variational quantum algorithms is take shallow circuits, parameterize it, estimate some cost function at the end of the circuit, and then we minimize this cost function. And we do that by combining the approach with a classical computer, whereby the classical computer instructs the quantum computer how to update the parameters such that the cost function is minimized. And so this idea was originally proposed to find minimal energy states of, let's say, a molecule, thereby finding the ground states. But it has been extended to so many other problems, for example, to combinatorial optimization problems, and so on. And it has grown into an entire field. You might know very well quantum machine learning, but it is very useful in solving a lot of other problems. And so recently, 3 review papers came out. I can highly recommend reading these. And we still, even though we can achieve value with these shallow quantum circuits, still we need to do something about errors. And quantum error mitigation is basically the cheaper version of error correction. It's a very new field. It has only emerged in the last few years. And the reason why it emerged is basically we have means of achieving practical value with these noisy quantum computers, but we have to somehow mitigate the effect of noise. And so generally, all these error mitigation techniques somehow want to only correct errors in the expected values. Because as I told you earlier, here at the end of the quantum computation, we just estimate expected values. You might recall that this sandwich quantity is the expected value of a Hermitian observable, and then it produces a real function. This is a function of the parameters. And in the end, the problem becomes a problem of parameter optimization. However, if our quantum computer is noisy, then we cannot exactly measure this expected value. There will be some bias that is contributed to this. And the way we want to deal with these, with error mitigation techniques, is we want to learn how error affects this single number, this expected value, and we want to correct it back. The simplest possible version to do this is the so-called zero-noise extrapolation technique. So what we do in this technique, we basically take a quantum computer, we estimate our expected value. Let's say the result is 0.5. We plot it on a graph. Then we ask the experimentalist, can you magnify the errors by a factor of 2? And it's actually very easy to do in an experiment. What the experimentalist cannot do is to decrease the errors by a factor of 2, because that might take years of work to build better hardware. However, if we tell the experimentalist to just magnify the noise, they can basically achieve it by, for example, making the gate twice as long. So we leave twice as much time for the system to relax. So thereby we magnify the errors. We again estimate the expected value. And so if we plot it on a graph as a function of the error value, then we can extrapolate back to 0 gate errors. And this approach is extremely simple. It might sound very, very simple, but it works surprisingly well. However, there are much more sophisticated techniques out there. For example, one can use the so-called quasi-probability technique. So in this case, what we do, we want to exactly learn how the error affects our quantum state. And we can learn this with tomography methods. In the end, we will obtain a matrix. It's similar to a unitary matrix, which represents, for example, a rotation. But this matrix now corresponds to the noise, how noise affects my quantum state. And we can formally invert this matrix and write it as a sum of quantum operations. And so we can conveniently implement these quantum operations with our quantum circuit. We will have a number of different quantum circuits, and we know the sum of these will give us the exact ideal quantum state. So we just run each and every of these circuits, we measure the expected values, and sum up the results. And basically, this is the quasi-probability technique. And this works surprisingly well if we have a good knowledge of the error model. But this error model might change during an experiment, because let's say the quantum computer heats up, and thereby this matrix will change over time, and we don't have the ability to all the time reconstruct this matrix. So we will have some we will not have a perfect knowledge of the errors. And so there are some other techniques. Generally, error mitigation techniques are really advantageous because they don't increase the qubit count. However, they have a huge disadvantage in that they significantly increase the sampling cost when compared to quantum error correction. The reason for that is here we cannot do anything about the quantum states. We just let the quantum states decay, lose information, and then we try to filter out all the errors, the errors that burden our expected values. And on top of that, we have additional non-trivial measures that we need to do. For example, this tomography, where we have to reconstruct the matrix that corresponds to our noise process. But generally, the greatest drawback was that none of these techniques can actually guarantee noise reduction. So I told you that, for example, in the quasi-probability technique, we cannot really guarantee that the matrix we use, we assume this is our noise model. We cannot really guarantee this is the exact noise model in an experiment. And so any deviation from this will result in an error. And we can generally not give guarantees, especially not exponential guarantees, like with quantum error correction. And so there's this new technique. It actually appeared in two consecutive papers. So one was by me and another by a team at Google. And the two papers report basically the same idea. The idea is relatively simple. What it does something similar to quantum error correction in that we now actually prepare copies of our quantum state. So I told you in error mitigation, we don't use any copies, we don't use any redundancy. So there we just use a single quantum circuit. But here we ask the question, what happens if we have the ability to prepare many copies? But here we do it very differently actually than in quantum error correction, because we don't entangle the copies before the computation. We actually run these quantum circuits, as I showed you here. We run these in parallel on, for example, many quantum machines. And at the end, we suffer from noise. That's why I write here we have a density matrix that comes out from every quantum machine or every quantum core. And these are completely separate. But now, when we are given with n copies of this computational state, we entangle them with a shallow circuit. And it turns out if we do this, then we can exponentially suppress the errors. We still cannot do anything about the extremely large measurement cost, but at least we can give guarantees that what we estimate here will be within a precise bound from the ideal value. And so for that, we only need to implement basically a shallow circuit that is relatively cheap. It's something that we can afford with even NISQ quantum computers. And what it actually does, it shuffles around the quantum computers. So it uses swap operations. And let's just go into the details a little bit. But in order to go into the details, we first have to introduce the density matrix. So you might have heard about quantum algorithms and quantum error correction, but in these, we usually assume that our quantum state is a pure state vector. So we can write this down as a vector. But it turns out if we are dealing with noise, we can no longer model our quantum system with just state vectors. We have to use the so-called density matrix. And so the density matrix is very, very convenient because what it does, it basically lists every possible outcome of the experiment. For example, we have a pure quantum state rho 1 that occurs with probability P1. So this could be that the computation runs perfectly without any error. Then we can add together different contributions. For example, rho 2 is now, let's say, an error happening to qubit 1 while executing gate 1 in our quantum circuit. And this happens with a small probability P2. And the density matrix is very convenient because we can take these exponentially many possibilities and sum them together into basically an average matrix. And this average matrix represents our quantum state, while also taking into account the noise. You already know that whenever we have a Hermitian matrix, we can diagonalize it. And when we diagonalize this matrix, we obtain eigenvalues and eigenvectors. And so here I show you the so-called spectral decomposition, which basically says that any Hermitian matrix can be written as eigenvalues times eigenvectors. And so here I distinguish the dominant eigenvector of the quantum state. It has the largest probability lambda. And so I say now probability because we know the density matrix has only non-negative eigenvalues which sum up to 1. And this also means that we can think about these eigenvalues as probabilities. And if we do this, then we obtain this very convenient decomposition. And it turns out that if we do this quantum circuit I showed you, this NISQ kind of shallow circuit, then it turns out this dominant eigenvector approximates very, very well the quantum state that we would obtain from a completely noiseless quantum computation. And so this is really surprising, but there's a reason why it happens. And the reason is that if we have large enough circuits, then what comes out is very close to white noise. And white noise will introduce no bias into this dominant eigenvector at all. And so just bear in mind that in the following slides, whenever I refer to this state, the ideal state, I actually mean the dominant eigenvector and not the ideal quantum state. And whenever I say an error state, so psi k, this isn't actually an error state the way we think about errors in quantum error correction, where an error might mean that a bit flip happens to qubit 1 while executing gate 1. This means something much more complicated, but still we can think about these as errors because these happen with some probabilities, and they are basically guaranteed to be orthogonal to the ideal or the almost ideal quantum state. And if we accept this, then we can run through this very simple thought experiment that illustrates why errors are so problematic. So if we have no error and we prepare n copies of our quantum state, then the most likely event is that no error happens to any of the quantum states. So this is the pure state that we obtain then. It's basically n copies of the exact same dominant eigenvector. And now let's say we want to measure the expected value of some operator sigma. We obtain the right value. This is what we need to use in quantum computing. However, if errors happen to my quantum state, then the second most likely event is that a single error happens to only a single register. So this is what we obtain. It's basically n-1 copies of the ideal state and one of these strange erroneous states, psi k. Now if we want to measure the expected value, we obtain something that we don't want to obtain. So it's an expected value that's different from the green one. This is what will cause generally the bias in our expected values. However, and this is now the trick, this is the main idea behind the approach. If instead of just simply measuring sigma, we measure sigma times the swap operation, where you might recall that the swap operation just permutes two quantum states, then basically the swap replaces this psi with this psi k. And then here you can see we have a scalar product between psi k and psi. But we said these are eigenvectors, so they must be orthonormal. And so that's why the result is 0. So basically, we filtered out this erroneous contribution. And if we generalize this to all kinds of reshufflings of the quantum register with the so-called derangement operation, then we can basically exclude any quantum state that breaks permutation symmetry. And so what this circuit does, it basically takes n copies of the same state, and it filters out everything that breaks permutation symmetry. However, it still includes everything that respects permutation symmetry. So what are those states? Those are basically the ideal computational state and copies of them, but also registers to which the exact same errors happened in each register. So these are also permutation symmetric. However, the probabilities are raised to the power of n. And so this means if we increase the number of copies of our quantum state, then we can exponentially decrease the errors coming from these events, these peculiar, strange events. However, it still does not mean that in the end we can guarantee that the bias in our expected value will be smaller than some exponential bound. We still need to work out some maths to guarantee that, because these are just probabilities and we have many of these, because we have exponentially many possibilities for errors to happen. However, if we work out the maths, this is what we actually obtain. So we measure the probability on a qubit, on the ancilla qubit here. And that probability gives us the ideal expected value, this green one, plus an error contribution here. And so first of all, what we need to do to recover this green expected value, we need to somehow remove this lambda factor. So it's the probability that no error happens, approximately. So in method A, what we can do, we just divide by this quantity, which we can estimate by replacing sigma with the identity, basically removing one gate from the circuit. But we can also estimate the eigenvalue of the quantum state. So there exist algorithms that can do this, or approximately do this. And so thereby we can basically remove this lambda and obtain our ideal, so our desired green expected value that we want up to this error. And it turns out we can guarantee that these errors, the red ones, are bounded by some exponential functions. So this is how theorists usually guarantee things. So they prove that there exists an upper bound and the error is always below that bound. And another interesting bit is that if we increase the entropy of our errors, meaning if we approach white noise, which can happen when you have extremely complicated quantum circuits, for example, random circuits, in that case, we can guarantee that we have something very close to white noise. And that's really good for us, because then we have very, very efficient suppression of the errors. And so I did some numerics. I'll just briefly show this. Here I show you how many copies I have, 1, 2, 3, 4. And if I increase the number of these copies, here is the bound, this solid line. It's a logarithmic plot of the errors. You can see that I guarantee that the error that we measure will always be below this solid line. And so here these bars, red and blue bars, show the actual errors that we obtain depending on what kind of sigma operator we want to measure. So these sigma operators can be Pauli matrices, or these can be Hamiltonians, molecular Hamiltonians. So depending on those, we will obtain different bars. But the guarantee here is that the bars will always be below the solid lines. And this is really good news, because it also means that if I want to achieve a particular precision, 10 to the minus 4, then I can look at this graph, how many copies I need. I need roughly 3 copies. So if I can do 3 copies of my computation, then I can guarantee that the errors will be below this, generally. So one thing I haven't yet explained is what are these strange reshuffling operations. So basically in the circuit we have only this is the chunky bit, where this is the operation that entangles all the copies. It entangles them because it's controlled on an ancilla qubit. So basically we create a superposition of our incoming state, which has all the copies in it. And it superimposes this state with the state where we reshuffle the orderings of the registers. How do we do that? So recall that when we want to permute quantum registers, then basically we use swap operations. And how many possibilities we have? Basically, permutations are a set of n-ordered elements. So we have n factorial elements. And derangements are the particular permutations that leave no element in place. So this means, for example, if, let's say, people sit around a table on chairs and everybody is told to stand up and find a new chair for themselves, but they are not allowed to sit in the same chair where they sat before. So that's a derangement of the ordering. And for that, we have fewer possibilities than for general permutations, but still we have an enormous number of possibilities when we have many copies. For example, for 2 copies, we only have one possibility. We basically have 2 people sitting in 2 chairs. They have to stand up and they have to find a new seat. So we just swap 1, 2 into 2, 1. However, for three copies, you can already see that we have 2 possibilities. We reshuffle the ordering 1, 2, 3 into 3, 1, 2 or into 2, 3, 1. So these are the 2 possibilities. But for 4 copies, we already have 6 possibilities. And that might be very useful when we actually want to do it with quantum computers. Because let's say we have a limited connectivity and we can implement this approach between, for example, different quantum processors. And if the quantum processors are in a line and only nearest neighbors are connected, then we know it makes no sense to, for example, do cyclic permutations. Instead, we can in parallel permute pairs, nearest neighbor pairs, and in just 2 operations, 2 parallel operations, we are done with the entire process. So how do we actually do this swapping? So what we actually need to do is swap register 1 and register 2, where in both registers we have possibly tens of qubits, or let's say hundreds of qubits. So what we do, we actually go qubit by qubit. So first we apply a controlled swap between the 2 registers, but only between qubit 1 and qubit 1 prime. So here the red region is register 0 and the blue region is register 1. So these are the 2 copies of my quantum state. As you can see, they implement the exact same computation on 2 copies. And now I implement the controlled swap just one by one, pairs of qubits at a time. And this is how I do it in general. And so already you can see that, well, if we have 50 qubits in the register, then we need 50 controlled swap operations. So this is a price we need to pay, but it turns out in the long run, the computation that we perform here will require a lot more quantum gates. And so we then also know that this part will pick up less noise. And so this is very good for us. However, many quantum computers will not be able to implement this controlled swap operation natively. So we have to do something about that. We have to implement these controlled swaps with native quantum operations. And so in the paper, I give some examples. This is how we can do that. For example, if our quantum computer is an ion trap, then it can implement XX, so-called Mellmer-Sørensen gates. So these are these here. These are Intangling Gates. And it turns out we only need 5 or 4 Intangling Gates to implement a control swap operation. And this is really good because this means that if we have 100 qubits in a computation, then basically we only need 500 or 400 entangling operations to implement this derangement process with 2 copies. Whereas in the main computation, we will likely need a lot more gates to implement anything meaningful with 100 qubits. And so here are some numerics that actually support these observations. And so here what is implemented is actually just a very small problem. It's a 6-qubit problem. We want to find the ground state of some spin ring Hamiltonian. And we do that by constructing a so-called ansatz circuit. So this ansatz circuit actually applies time evolutions for some given times, parametrous times, gamma 1, beta 1, gamma 2, beta 2, and so on. And so these timings are my parameters. in the quantum circuit. And in a variational quantum algorithm, we want to optimize these parameters, these timings. And how do we do that? We need to measure the energy at the end of the circuit. And by minimizing the energy over these parameters, we can hopefully we can find the ground state of this Hamiltonian. But the problem is that in a real application, these gates are noisy. And in the end, at the end of the circuit, what we measure is actually a noisy expected value. And that's why we need error mitigation to get more value out of the process. Or we can think of somebody just gives me the parameters that optimize this circuit. It's still not very useful because I still need to estimate the expected energy to good precision. And if I implement this as that circuit, in this particular very, very simple, basically the simplest possible example, I need 360 Intangling Gates. And for a 6-qubit problem, it's quite a lot. So these gates pick up a lot of noise. However, if I can do 2 copies of these circuits, meaning I have 2 6-qubit quantum computers, and I can then hook them up with some quantum link, so we can communicate between the two quantum machines, then I can implement the derangement operator. And it turns out that only requires 30 entangling gates between the 2 copies. And that's more than an order of magnitude less than what we need to do the ansatz circuit. And so that's why it will pick up significantly less noise. And so these numerical simulations very nicely confirm this. So the red line here shows what happens if we do no mitigation at all. The x-axis is now what is the expected number of errors that happen in my variational circuit. And so in practice, we will probably be interested in this region. And actually, we cannot really go beyond more than, let's say, 10 errors per circuit, because at that point, the whole procedure breaks down, because we need to perform so many measurements to estimate the expected value that it becomes prohibitive. So in practice, we are basically limited to this region, and we can only achieve this region if we have sufficiently low error levels in our gates. And for that, we actually need very good experimental hardware to do that. But let's say we have a sufficiently good quantum computer, so we can compute in this region. We still have a lot of error. So I show the error in estimating the energy here. So I told you zero noise extrapolation is an approach that works surprisingly well. As you can see, indeed, it works really well. So it reduces the errors by more than an order of magnitude, which is great. However, if we do the derangement trick, so the blue dashed line shows what happens if we have no errors in the derangement process, then you can see we not just reduce the errors by a constant factor, we actually have an improved scaling. And this is because basically we are now able to square the errors. And if the error is small, then the square is extremely small. And so you can see we have on this log-log plot, we have a different slope, meaning that we have a different polynomial order in which the errors vanish. And it's actually an idealized view of what's happening, because we also have errors in our derangement circuit. And the magenta line actually simulates this, what happens if we actually implement in an experiment with noisy gates these swap operators. And you can see that we don't really have this fundamental improvement. We have the same kind of slope, but still we can improve by a huge absolute factor, so many orders of magnitude. We can improve on the error mitigation free expected values. So this is really great news. However, if our quantum circuit is very, very noisy, for example, if we are in this region here, then we need to perform more and more. We need to perform the computation on more and more copies. And that's the really great news here, because we can still reduce the errors if we have the ability to prepare more and more copies. it's actually still not the full story. So the main drawbacks of this technique is that it cannot do anything about coherent errors. And so you might expect that these coherent errors are the ones that, for example, happen because we have a miscalibrated rotation angle. And so we leave our quantum state can be written as a superposition of some, let's say, incorrectly rotated state. But we can introduce incoherent errors to the dominant eigenvector even without, we can introduce coherent errors to the dominant eigenvector even without miscalibration of angles, rotation angles. It turns out even if we have a fully incoherent error model, for example, depolarizing noise, even in that case, we can shift the eigenvectors of our quantum state. And this is a highly peculiar feature of quantum mechanics. And there is an entire paper just about this point where I derived general guarantees how big this effect can be. But it turns out it's a really small effect. It's something that we might not even be concerned with in practice. Because here, with the gray dashed lines, I show you what happens if I have infinitely many copies. For infinitely many copies, I can exactly recover expected values in the dominant eigenvector because I have these exponential guarantees on the errors. But as you can see, since the dominant eigenvector is not exactly the same as our error-free computational state, there is going to be some error floor. However, this error floor is really, really small. And in principle, in practice, we would be happy with such an error floor. So we're not very concerned about that. So the other great disadvantage of the technique is that it increases the number of measurements by a significant factor. But this is something that's not unique to this technique. It's generally true for all mitigation techniques. And the reason for that is with quantum error mitigation, we cannot actually correct the errors. We can just mitigate their effect. But that has an exponential price that we need to pay. And so for all the simulations I showed you, I actually used Questlink. And so this is a C code that is very, very efficient. It's one of the most efficient simulators out there. And we have a Mathematica front end to this. So you can very conveniently use this from Mathematica. So I can recommend trying this out if you want to simulate quantum circuits. And thank you very much for your attention.
Thank you very much, Bálint. That was a fantastic talk. I'm pretty sure everyone's giving a round of virtual applauses. Subhat, I believe that you've been compiling some of the questions. Care to share them here in the chat?
Great.
Mm-hmm. See, then I can read them over. All right. So we have the first question that says, do you see any prospect for partial error correction, having just some error corrected qubits?
I think this is still an active area of research. I don't have anything. I don't really have an obvious idea about that. So one has to look into that. So I can't really answer this question. It would be certainly very interesting to somehow combine best of both worlds, but I would expect it would be highly non-trivial to do.
Right. Yeah. No. It's an interesting question. We've also had similar thoughts, but I agree. It's still very much active area of research. Mm-hmm. So let's go to the second question. Does the ESD work in a similar way to the open quantum system approach, where the row states are used as ancilla?
So I have to first understand the question.
Work in a similar way to open quantum systems.
So here the ancilla is this single bare qubit. So we only need a single ancilla qubit to perform this.
But I think they're asking if the row states are used as ancillas here.
Mm-hmm. So actually all the row states are in some sense equivalent. So they are all computational qubits. They all perform computations and actually the same computation.
So if the person that asked this question, they want to clarify or ask a follow-up question, please feel free to write them.
I might. So it could mean that there are algorithms for simulating, for example, open quantum systems, or discovering excited states of spectra. And for that, we have two copies of the system, but one copy is in some sense an ancilla, where when we want to explore excited states, then we first discover the ground state with just a single copy. We store it in an ancilla register. Now we use this ancilla register to all the time compare this ancilla ground state with the state that we prepare here, to always project out the ground state, thereby finding an excited state.
Right.
And so for that, we need to use the so-called swap test, which is basically the same thing, what I'm showing here, except in the swap test, we don't have a sigma here. If we just have two copies, and not even copies, so the two rows can be different, then what it returns is basically the overlap of the two states. So that's right. So to answer your question, it is a generalization of that. So it incorporates the swap test as well.
Right. I guess that here you're just projecting back into the subspace of the ground state rather than the first excited state, right?
Exactly, yes.
Right, perfect. So we have our third question. By increasing the number of copies, the error is reduced. But at some point, does it become inefficient to have a large number of copies?
Yes, you're absolutely right. Yes. So in the simulations, I only show the case for two copies. So this green dashed line is only the ideal value that we would obtain with perfect swaps. The reason why I do this is that I have a 6 qubit problem. I have two copies of that, so I have 12 computational qubits plus an ancilla. That's 13 qubits. And to classically simulate that, it's extremely demanding, because if you want to simulate noise, you have to use density matrices. That means basically you have to perform a 26 qubit simulation, and that's very costly. So I estimated how long it would take to go up to 7 qubits, and it would take just a month of computation with one of the very, very complex machines.
Oh, wow.
And so it's not. I believe it's not worth doing that. But if I could simulate that, if I would dedicate a cluster for just simulating this for a month, probably I would simulate a 3-copy example, and there I would see the noise I pick up is worse than with the 2-copy case. Obviously, because I don't just have a single swap operation, I have 2 swap operations now, so I pick up twice as much noise. So you're exactly right. If I do a large number of copies, I proportionally pick up more and more noise. So I don't really want to do a lot of copies. However, the good news is that you can see that already with 3 copies, I'm very close to this noise floor. And with 4 copies, I'm basically at this fundamental noise floor.
Right.
And so in this other paper, I actually proved that we basically need at least 4 copies to reach this error floor. So in practice, we probably don't even want to go beyond n equals 4. But even n equals 4 might be a demanding task with NISQ.
Right. And I guess that this actually points out and connects really well to the fourth question, which you were mentioning that the more copies you have, the more noise you can pick up. And the fourth question is, how does the noise in the circuit that does the error mitigation affect the mitigation protocol in itself? So I guess that the question is,
it's exactly the same point. Yes. So basically, the noise in the error mitigation technique brings this blue line up to the magenta line, and so it will degrade the performance. But it turns out by not by a lot, and the reason for that is in the error mitigation technique, in this particular example, we only have 30 gates that implement the mitigation, whereas we have 360 gates in the main computation. And so this is a worst case scenario for mitigation, because if you want to do, for example, quantum chemistry, or let's say you want to do the Hubbard model, so it has been estimated that to compute the Hubbard model for 50 qubits, so it's a kind of an entry-level problem into practical quantum advantage, we need about 50,000 Intangling gates. That's quite a lot. Whereas for the derangement, for 50 qubits, we only need a few hundred gates. So we have several orders of magnitude difference in the requirements in the gates.
Right. No, that's great because, and so I just see that a question just popped up in YouTube that is not here. Let me read it for you. Do you think error correcting codes will improve enough in the future to make quantum computers with large number of qubits physically feasible?
I think so. Yes. So there is generally hope around this, and then there are still new ideas coming out. So so there is this far future. We know a lot about error correcting codes. It seems very, very far, but there is still active research developing these techniques, and that far future seems to come closer to us, whereas we are building the bridge from our side, so we have more and more advanced techniques to use machines without error correction. So hopefully we can close the gap soon, within the next couple of years, or who knows, maybe even a few decades.
Right. And I see that Alvaro, one of our co-organizers, is saying there are things like CAD encodings, right, that are more hardware efficient.
So I guess CAD encodings, one might refer to the CAD qubits optical systems. So thereby we basically have superpositions of coherent states. And so indeed they are more qubit efficient in some sense. Also superconducting, maybe I'm just not aware. So there are so many error correcting codes. Actually, the one I showed you here, color codes, it was thought to be one of the cheapest ones to implement, and it's very well suited for ion trap systems, because ion traps have basically arbitrary connectivity. And so it depends highly on the platform what kind of encodings you can implement.
All right, so I think those are the questions that I had. I just had one specific question.
Sure.
Maybe it's more about the intuition. So you said that 4 copies of your state is enough, and you can sort of prove that that's what you need to reach the floor. Is there some intuition why 4 specifically rather than 3, 5, or I would have expected that there's like a limit on the very large number of copies, right?
I see. So it's hard to say what's the intuition. Basically, where it comes from is, first of all, we have bounds here. We can guarantee that if I can produce this many copies, then the error will be below this bound. Now, from this other paper, I have guarantees that if I have this kind of noise, or this amount of noise in my system, then I can guarantee that the mismatch in the dominant eigenvector will be smaller than this value. And then from that, I can guarantee that its effect on the observable will be smaller than this, given the amount of noise. And now I can combine these two bounds, basically. So I can say, if I have a sufficient amount of noise, like in the one we are used to in practice, like a circuit error rate of 0.1 or 0.5, then I can guarantee that the coherent mismatch will be below my error bounds if I have at least 4 copies.
Oh, that's interesting. I remember reading this paper, and that just sort of went over my head. So it's really great to see this, because I always had this in my mind that I wasn't sure how many copies you needed for ESD. But thanks again, Bálint. That was a great presentation. I'm pretty that our students really enjoyed it. There's a lot of things that you've been mentioning here that we've seen throughout the course, so I'm pretty sure that they're pretty caught up on to follow a lot of it. So thanks again, and it was a pleasure to have you.
Thank you. Thanks for the invite. Bye.
All right. Take care.
You too.